All right, welcome back. Today we're jumping into something that's literally all around us, but it often feels like total chaos, and that's randomness. We're going to explore this incredible mathematical tool that actually helps us find predictable patterns inside all that chaos. We're talking about probability distributions. So, how in the world can we make sense of things that seem to have absolutely no rhyme or reason? I mean, think about it. The number of customers who walk into a store each hour, the chance of getting a rare item drop in a video game, even something as technical as data packets arriving on a network. It all just seems unpredictable. But what if there was a way to mathematically model that uncertainty? Well, that's exactly what we're going to tackle today. So, let's start at the beginning and build our foundation. I want you to think of what we're about to discuss as a kind of blueprint for chance itself, a map that helps us navigate the entire landscape of random possibilities. At its core, a probability distribution is really just a special kind of mathematical function. Its one and only job is to assign a probability to every single possible outcome of some random event. So it's not about what did happen in one specific case, it's a theoretical model of everything that could happen. And the great thing is, for any distribution to even be valid, it only has to follow two super simple fundamental rules. First, you can't have a negative probability. It's always 0 or more. Makes sense, right? And second, if you add up the probabilities of all the possible outcomes, they have to equal exactly 1. Or, 100%. This just means our model has to account for every single possibility. Now, this brings us to a really crucial distinction, the difference between reality and theory. On the left, a frequency distribution is what you get when you go out and actually collect data. You count how many times each outcome happened in your sample. But on the right, the probability distribution is the abstract theoretical model of what we expect to happen in the long run. So frequency is what you observe, probability is the blueprint. Okay, so not all random variables are created equal. Some things in life we count and other things we measure, and this simple difference splits probability distributions into two major families. So on one side, we have discrete distributions. These are for things you can count in whole numbers, like the result of a dice roll or the number of defective products in a batch. On the other side are continuous distributions, and these are for things you measure on a scale, like height, weight, or temperature, which could technically take on an infinite number of values within a range. All right, now for the fun part. Let's meet the stars of the show. I want you to think of these common distributions as a cast of characters, and each one has a very specific job and its own personality. These are the greatest hits you're going to see over and over again in statistics and data science. First up, let's meet the binomial distribution. This is your go-to expert for any situation where there are only two possible outcomes. We're talking yes or no, success or failure, heads or tails. So what's its specific job? Well, the binomial distribution steps in when you have a fixed number of trials. Say you flip a coin 10 times. Each of those flips is independent, each one has only two outcomes, and the probability of success, let's say getting a heads, is the exact same for every single flip. When all those conditions are met, the binomial distribution can tell you the precise probability of getting, for example, exactly 6 heads out of those 10 tosses. Let's look at a quick example to make this real. Imagine you draw 2 cards from a deck, but you put the first one back before drawing the second one. What's the probability of getting 0 aces, 1 ace, or 2 aces? Well, this table shows you exactly what the distribution does. It assigns a precise probability to each outcome. And hey, notice how they all add up to 1? Just like our rule said they had to. Next in our lineup is the Poisson distribution. Now, if the binomial distribution is all about counting successes in a set number of trials, Poisson is about counting how many times an event happens over a specific interval of time or space. Yeah, the Poisson distribution's specialty is modeling event counts. It's perfect for questions like, how many customer service calls does a center get per hour? Or how many people visit a website in a minute? The key things it needs to work are that we know the average rate of these events and that each event happens independently of the last one. And to see its power in action, think about this. If a bakery knows they sell an average of 5 cupcakes per hour, the Poisson distribution can calculate the probability of selling exactly 3 in the next hour. And that probability, it turns out, is about 14%. How incredibly useful is that for planning your inventory or figuring out staffing? And now, for the superstar, the one you have definitely seen before, even if you didn't know its name. Let's meet the normal distribution. This distribution is famous for a reason. It just shows up everywhere, in nature and in statistics. Its job is to describe data that naturally clusters around a central average. It's perfectly symmetrical, it's bell-shaped, and the further you get from that center peak, the less likely the outcome is. Things like adult heights, blood pressure, measurement errors, even test scores, they all tend to follow this classic pattern. It's so common that it has its own famous nickname, the bell curve. Its shape has become a true icon of statistics, and it's a powerful reminder that so many seemingly random processes in our world actually follow a very predictable and, frankly, elegant pattern. Okay, so we've met the characters, but why does any of this matter outside of a math class? Let's connect these abstract ideas to the real world, specifically how probability powers the technology that we all use every single day. Seriously, the applications are incredibly diverse. In machine learning, distributions are the backbone for handling uncertainty and predictions. In networking, the Poisson distribution is a classic tool for modeling data traffic to prevent websites from crashing. For security, cryptography relies on uniform distributions to generate truly random numbers. In computer vision, they help algorithms make sense of noisy image data. Even in software testing, distributions can help predict the likelihood of bugs showing up. They are the invisible engine behind so much of our modern tech. So after all of that, what's the big idea? What's the one thing you should take home with you? Well, it all comes down to understanding the predictable nature of chance itself. And this is the main takeaway. A probability distribution will not tell you with 100% certainty what the next card drawn from the deck will be. But it does something far more powerful. It describes the entire landscape of possibilities and tells you exactly how likely each part of that landscape is. It's about understanding the whole system, not just predicting one single event. And that leaves us with a final thought to chew on. If we have the mathematical tools to find clear patterns and structure inside of randomness itself, what does that truly mean for the future of prediction, of forecasting, and for our ability to manage an uncertain world? Thanks for watching.